Problem number 3 here about a piano being launched from a certain height and going a certain distance. We know the y uh, component of the initial velocity only. Um, this one doesn't have quite as many parts to it. It's one of the more, I guess it's a little bit different from problems we've worked in the past. So here is the piano, and it is launched. We don't know anything about the angle. Doesn't tell us. Um, we know it's not vertical. It's not launched vertically, um, and it's not launched horizontally because it does travel some distance, and it does um, tell us there's an initial y component to the velocity. Okay, so if you just threw it straight up, then it wouldn't go any distance horizontally, but we know it travels 30.1 meters horizontally from start to finish, and we know that it falls a distance of 10 meters from here to here. So we're going to be asked about this highest point that it reaches, the angle when it was launched, and the final velocity, the magnitude of that final velocity, as well as time. So let's look at time first. We know the acceleration in the y direction. Always, always, always. We know the initial velocity in the y direction because they told us, 13.59. And then when it hits the ground, we don't know that velocity, but we don't know how long it takes, but that's what we want to know. But we do know how much y changes from the time it's launched until the time it hits the ground. It's going to go 10 meters, but you have to be very careful to make sure that's negative because it travels downward. That's the initial velocity. Okay, so we do have an equation that uses all of these things in it, and that is equation number 3. And I'll point out right now that having these 3 things, we could find V final, and we could avoid equation 3 if we wanted to. But I don't want to. So here we go. Negative 10 is equal to the initial velocity in the y, 13.59 t, plus 1/2 times negative 9.8 times t squared. We have a lot of options when we get to here. Okay, this is a quadratic. We can't just divide the t's away. We can't just square root the t's away. We can solve it by graphing, which is perfectly fine, and I think the easiest way. We could also add 10 to both sides and then solve it using the quadratic formula, which in my opinion is by far the most tedious way to do it. But here's what I would do. Go to the calculator, go y equals, and I would type in negative 10, because I want to know when the height of this thing is going to be negative 10. And then I would type in the other side of this, 13.59 x, because I can't do t, minus 4.9 x squared. 4.9 is just half of 9.8. We use that so much that it becomes something that's helpful just to memorize. Okay, I'm going to change my window a little bit. I want it to go a little bit lower, and I'll hit graph. So the red line represents the object being thrown, and it's up here on this cliff, and it goes up, and it comes back down. Here's where it has a height equal to the cliff height, the 10-meter height, and then it keeps falling, and this point right here is where it is 10 meters below where it started. We could find that by hitting second and trace. That thing is an intersect. And it says first curve, but we want to actually move closer to that intersect. We don't want this point over here. That's negative time, which doesn't even make sense. Move your cursor until it's over closer to that intersection and hit enter 3 times. We get 3.38 seconds. That's the time of flight. So what is the highest point that the ball reaches? So again, we're going to use these, the initial y velocity and the acceleration, but instead of using delta y, because that's what we want to know. Okay, so now we want to know what delta y equals. we don't know at the moment how much time it takes to get to the top, but we do know what the velocity is at the top. So if we treat the launching point as the initial point and the top as the final point, the final velocity is 0. We don't have time, so we're going to use equation number 4. Final is 0, initial 13.59 squared, negative 9.8, delta y, negative 10. Oh, sorry, not negative 10. I was thinking about how I was going to get a negative answer. Whoops. Delta y, sorry. Delta y is the thing we don't know. It's not negative 10 anymore. Okay, but that is a really common thing that I see when people are plugging things in. They put negative 10 in, but negative 10 is not the change in height from here to here. It's the change in height from beginning of the launch until it hits the ground. So we want to find delta y. We're going to move this 13.59 squared to the other side, and it'll be negative. Then we're going to divide by 19.6. We get 9.4. meters. So that's the highest point compared to where it launched. It's going to be 9.4 meters higher than it used to be. But it was already 10 meters off the ground, so I'm going to add 10 and get 19.4 meters. Now let me show you a cool thing about the graph. Back in Algebra 2, we talked a lot about intercepts. We talked about maximums, minimums, intersections. So let's see what happens if we find this maximum point. This one. So I'm going to go left bound of that maximum, and I'm going to use the cursor to go to the right side. At 1.38 seconds, that's when it gets to the highest point. Look at that, 9.4. So there are no calculations required. You graph it, this shows the height. It's going to be 9.4 meters above where it was, and that's the answer we got here. Pretty cool. What angle was the object launched? Okay, we need to know, if we want to know the angle, we need to know the initial x velocity, and we need to know the initial y velocity. We already know the initial y velocity, but we don't know the x, and that's what we need to find this angle theta. So the initial x velocity is linked to the change in position over the amount of time. And that's where we finally get to this 30.1 meters, something that we know, divided by the total amount of time it takes to go that 30.1 meters. And we get the final, or the final and initial x velocity. It's 30.1 divided by 3.38. You get 8.9 meters per second. So the angle that it was launched is just the tangent inverse of the opposite side, which is that 13.59 initial velocity over 8.9. The final velocity, that's just the magnitude of that velocity, so I'll put little absolute values around it, is equal to the final velocity in the y direction squared plus the final velocity in the x direction squared. So v final in the x direction, or in the y direction, did we find that? Darn, we didn't find that. Whose idea was that? Okay, v final in the y direction is equal to v initial in the y plus at. Initial in the y, as I'm calculating this, just realize that once you've got one thing, it's not very hard to find the rest of them. And so I can pretty quickly find this 13.59 minus 9.8 times 3. Negative 19.53. So that's what I'm going to put here, negative 19.53 squared plus 8.9 squared is equal to the final velocity squared. So watch how I do this. I'm going to square that number, super easy. I'm going to go up and grab this number, that's the x velocity, square it. And then I'm going to square root that answer. And I get that the final velocity, the magnitude of that velocity, is 21.5 meters per second. We've made it through the group work questions. Cheers if you've made it all the way through this with me.